back because some of you were not here last time, so let me just show the method again. So this is a function, and of course we see it's continuous, and by the intermediate value theorem we can determine a 1 unit interval, like, I don't know, 1 to 2 or -3 to -2. 1 unit interval where the function is 0 by the intermediate value theorem. So here's the root. I'm going to take a unit interval, but I'm going to make it as big as possible so I can explain. So this is the 1 unit interval for us. So let's say a comma b. So I can start either at a or at b. So this is what I'd like to really call the initial value. I pick this, and I have to make sure that f prime of x0 is not 0. Otherwise, the method will not converge. It will not give us the solution we are looking for. So Newton said this. Okay, so this point here is x0 comma 0. Draw a vertical line and determine this point, which of course is x0 comma f of x0. It's on the function. From here, draw a tangent. I'm going to draw it so it does not get too close because I want to show the mechanism. So I'm just going to say it's here. It should be a little bit closer, but I want to show at least 2 iterations. Okay, so this is the tangent at this point. And the tangent at this point crosses the x-axis, and this is what we call x1, the first iteration. I'm okay if you want to go with the book and say, this is my first iteration and this is my second. That's fine. Doesn't matter. I don't think that this is an iteration because I picked the value. I didn't calculate it. So that's why I call it the initial value. I don't call it the first iteration. But if you agree with that, with the book, I'll agree with you. Okay, so now this line has the slope f prime of x0. But also, because this point is x1 comma 0, is f of x0 minus 0 over x0 minus x1. y2 minus y1 over x2 minus x1. So this is the same with f of x0 minus 0 over x0 minus x1. When we solve this equation for x1, we will get, and you can do the algebra, we will get x0 minus f of x0 over f prime of x0. I didn't mean to put that sign in there. Okay. Obviously, this number is a better approximation of what I'm looking for than the initial value. Very clear. The initial value is far away, and this is closer. Okay. We want to continue. We will continue in exactly the same way. We'll draw a vertical. We will determine this point. Of course, this is x1 comma f of x1. And like before, I will draw a tangent. I will draw the tangent. Again, I'm going to try to not get too close. And I'm going to get the second iteration, x sub 2. Of course, this point is x sub 2 comma 0. And I continue and on and on and on and on. And I will get as close as I can possibly get to the solution that I'm looking for. And how will I determine x2? Is exactly the same procedure in which I have that x2 is now x1 minus f of x1 over f prime of x1. And I can continue forever. The n plus first iteration will be x sub n, the previous one, of course. X sub 2 is the previous one. X sub 1 is the previous one that I call the initial value, minus f of x sub n over f prime of x sub n. And this is Newton's method. So two things. I have to make sure that this, my initial value, the initial step, does not, I don't pick A or B so that f prime of those numbers, one or the other, is 0. Because if this is 0, I will never determine x1. So I will never get anything. That's one thing. And the other thing is, which is much rare, is what if there is a minimum or a maximum between the initial value and the actual solution? So if I have a minimum or a maximum here, the method will not converge. That's why we insist that this interval is like the interval for the intermediate value theorem, not more than 1 unit interval. You can make it smaller. If you know that this is 1 and this is 2, you can start at 1.5 if you want. Maybe 1.5 is here, doesn't matter. But not further away, not an interval that is more than 1 unit. Okay, so we would like to, so two problems, right? Potential problems. F prime of x0 cannot be 0. And make sure there is no max min between the initial value and the solution we are looking for. And now let's choose a couple of problems, because I want to show you how to do this with a calculator, of course. We're not going to do this by hand. I need to probably work on this at least on two different problems. Okay, so I'm on Newton's method. It's page 355. So let's start with something like 17. Feel free to choose if you want. Sine x equals x minus 1. And the question, use Newton's method to find all solutions. No. So when you do the homework in WebAssign on this section, I don't care for all solutions. One solution, and I'll give you the credit for it. For each equation, I want one. Because if you know how to solve one, I really don't need you to show that you know how to solve this for the second one and find the third. No, no. For each problem, one solution, the one you pick, and then just tell me and I'll give you credit for the whole problem, okay? So one solution. Here it says, use Newton's method to find all solutions of the equation correct to 6 decimal places. So we want 6 decimal places. Okay, so we're going to find one solution. So here are the steps. So please, we have to find an interval first. So we have to first use the intermediate value theorem for continuous functions. Okay, so first step, I have to have a function, not two functions. So solving this equation is the same with solving this equation. Solving this means solving this, same thing. But now in part 1, I do have a function. I'm happy. I can immediately find its derivative because I will have to use it. So this is cosine x minus 1. In step 2, I will have to say, because this is continuous everywhere, linear, continuous everywhere. So f of x continuous as a addition, subtraction of continuous functions. That's good enough. We know sine is continuous everywhere. We know this is continuous everywhere. Next, I put it in the graphing calculator. So we have sine x and then minus x plus 1. Okay, and I will go to second table and I plug in some numbers. Let's say I'm going to start with -1. I'm going to continue with 0. I'm going to continue with 1. I'm going to continue with 2. Make sure, since I didn't say that, but make sure that the mode is in radian mode. Mandatory, radian mode. Let's check. Okay, I'm okay. Because of sine. So I found, yes, go ahead.
Will Newton's method always be on like sine, cosine, tangent, like that stuff? Will it always be radians?
Always radians. Every time in calculus, every time we talk about a trig function and a value outside of the trig function. So let me explain this. This is a very good question. Okay, let me stop here for a second. We had this discussion when we talked about approximations. So if I have tangent 45 degrees or tangent pi over 4, so inside a trig function, it doesn't matter. The answer is still 1. But if I have, let's say, like we were trying to, let's say, approximate this, right? We wrote it's approximately tangent 45 degrees plus f prime, which is secant squared 45 degrees times -1 degree. I can't leave it as -1 degree outside of a trig function. I have to multiply by pi over 180 because I have to make it into radians, turn it into radians. It's mandatory. Now, if it's inside a trig function, who cares? The answer is the same. But if a degree is outside of a trig function, it has to be changed into radians. What happens here? Okay, because I have an x outside of a trig function in the same function, it's like here. I have to have radians. So better safe, unless you are given something in degrees, okay? You should not change the mode. You should always have it in radians. Okay, very good question, thank you. So I realized that this function is continuous, and at 1 is positive and at 2 is negative. So there must be a solution by the IVT for continuous functions. There must be a c between 1 and 2 such that f of c is 0. And I have to write that down. So I will say here, f of 1 is positive, f of 2 is negative. Then, by the intermediate value theorem, there exists a c in the open interval 1, 2 such that f of c is 0. This is guaranteed by IVT. If it's continuous and it changes sign, at 1 is positive and at 2 is negative, I don't even care to write the numbers. It doesn't matter to me or to you, to anybody, right? It doesn't matter. F of 1 is positive, f of 2 is negative by IVT. There must be at least one c in the open interval 1, 2, not 1, not 2, careful, such that f of c is 0. Okay. In step 3, I create Newton's function. So, in step 4, I call this Newton of x, which is, it's x minus f of x over f prime of x. X minus f of x, I copy it, sine x minus x plus 1, and I already have the derivative, cosine x minus 1. This is the function that I will put in the graphing calculator. Exactly as you see it. And after I do that, in step 5, I will consider it x sub 1 or x sub 0, whatever you want. It doesn't matter to me. I consider it an initial value because there are no calculations. So I can start at 1 or I can start at 2. It doesn't matter. As long as the starting point, let's say I start at 2, as long as f prime of 2 is not 0. Is f prime of 2 0? Of course not. Cosine 2 radians minus 1 will not be 0. So I'm okay with this. So now let's enter this function. Don't erase anything. Don't delete anything in the graphing calculator. Let me show you why. So go to y equals. You already have the top of the fraction. Don't delete this. Just second and insert, put an x, put a minus, put left parentheses, go all the way, put another right parenthesis, and now divide by, in parentheses, the denominator, which is cosine x minus 1. Okay? And close again. See what I did? Minus 1. Okay, so cosine x minus 1 in the denominator, and everything else is correct. So now, go to second and quit. Go to variables. Go to the y variable. Select function y1. That's where my Newton's function is. Press enter. And as we discussed, this is my initial value, and I want to get a number. This is x1. I copy it. 1.935951152. Here's what I do next. Second an entry and overwrite the 2 by the previous answer with second an answer. So now in the same function, I want to put in this to get x sub 2. So x sub 2 is 1.934563874. And now it's done. All I have to do is just repeat. I don't change anything anymore. So x sub 3, 1.934563211. I was asked to use 6 decimal places. So 2, 4, 6, they already repeat. So I don't need this anymore, because the 6 digits already repeat. So this is good enough for me. So I don't need this because I have 6 digits. Of course, you can increase 3 to 4 because this is 8, but that's all I need. So the method converges very fast for this function. For others, maybe if I start at 1, it will take longer. Maybe if I start at 1, it will take less. I don't know. We can try. But it's not important. Again, you can say, why are you doing all this? Okay? You can put any function in here. You go to second and calc, and you use the 0, and you get the number. True. Yes, I can do that. So I can go to this, clear everything. I have sine x minus x plus 1. But then this will not be calculus, and we will not appreciate Newton's method. Okay, so I go to second, and how can I want the 0? Again, I have to graph the function, so the graph is not, let me go to the standard. Okay. Good. So I want the 0. So second and calc, I want the 0. I want, that is a good left bound, that's fine. I want the right bound, whatever. And just give me the solution. And I have it. It's exactly what we just obtained. 1.934563. Okay? So I don't know which one is, I guess Newton's method may have some minor error after the 6th digit. In case this is good enough, I'm not sure. But the reason we're doing this